All right, good morning. So what I'd like to talk to you about first thing this morning is another method for basically looking at molecular dynamics simulations and trying to understand some of the long time scale behaviors of these systems. And we'll see how we can analyze those long time behaviors from hopefully much, much shorter molecular dynamics simulations. And the way we're going to do that is through a model which we call the Markov State Model, sometimes called a master equation model or a network model. Okay, so just as a recap, you're probably all familiar, but how we perform molecular dynamics simulations is we represent first all the atoms of the molecule and surrounding solvent. Later this afternoon, you'll learn about some implicit solvent methods where you can implicitly represent the surrounding solvent, but here I've just shown it with the solvent shown explicitly. We then model the forces acting on these atoms. These forces can be things like constraints on bond lengths and bond angles, various steric constraints that say two atoms can't be co-located in the same space, or things like different charge interactions. And again, I'm saying things in terms of atomistic simulations, where we represent all the atoms of the molecules, but these methods could easily be applied to coarse-grained simulations as well, where we would have the coarse-grained beads and the forces, as Greg described yesterday, which we can calculate, which are acting on those coarse-grained beads. We then take Newton's laws of motion and we simply integrate them forward in time to see how the system progresses in time. And the challenge with molecular dynamics, which were some of the methods which Aaron and Benoit had talked about last time, the challenge is that we need a very small integration time step compared to the time scales of the motions in which we're interested in. And the reason for this is that the forces acting on these atoms are very nonlinear. And so in order for this integration to be both stable and accurate, we need to use small time steps to see how it moves. Otherwise, if we took two large time steps, for example, we could have two atoms collide with each other in the next time step. In terms of timescales, what that means is that the typical MD time step for atomistic simulations is on the order of femtoseconds, or 10 to the minus 15 seconds, because this is the time scale on which bonds vibrate. Using various types of computational methods, which I'll show on the next slide, we can now perform molecular dynamics simulations on the order of microseconds. But the challenge is that the systems which we want to study, processes like folding or other types of assembly, could occur on the order of milliseconds to seconds. So we still have this large timescale gap which we need to bridge from what we can perform from molecular dynamics to the systems which we want to study. And again, as Aaron had talked about yesterday, methods like transition path sampling could be applied to try to bias our simulations toward these rare events which would occur on these longer timescales. I'm going to talk about a different method that just tries to use bulk molecular dynamics simulations to also get at these longer timescales. Okay, so as I said, we can now, it's pretty routine to do large-scale molecular dynamics simulations using various methods. So as a graduate student, I worked on the project Folding at Home, which you might be aware of. It's a large distributed network where volunteers around the world essentially donate their down computer time to perform molecular dynamics simulations. And currently, Folding at Home has, I believe, around 300,000 volunteer computers from around the world to perform molecular dynamics simulations. Using a model like this, it's very easy to run multiple simulations in parallel. You can tell each of your volunteer computers run this molecular dynamics simulation for some length of time, but you can't run very long trajectories because you don't want your volunteer computers communicating with each other. You only want them doing independent simulations. At the other end of the spectrum is the new supercomputer which D.E. Shaw built, the Anton supercomputer, which has specially designed hardware which essentially only performs molecular dynamics simulations. And they developed some new algorithms to figure out how they can very efficiently parallelize these molecular dynamics simulations to run single long trajectories much, much faster. So the idea, as I said, with molecular dynamics simulations, we have all those atoms of the molecule in the solvent, all those forces acting on them, and we need to calculate how these will move at the next time step. So they've figured out some ways to efficiently partition those molecules, those atoms, and the forces acting on them between the different processors in their supercomputer, and to do that in a way that they don't need to communicate very much, and they can run individual MD steps much faster, and therefore generate single trajectories that are very long, faster than you can on a normal computer. Sort of in between are things like the Blue Gene machine, which is a general purpose supercomputer, so it can perform any type of computation, but it's sort of optimized to do molecular dynamics, or your own homegrown desktop cluster, which you could put in your closet and run various things. And so using this, people can typically generate, I think on Anton, they have molecular dynamic simulations on the order of hundreds of microseconds, if that's correct. So relatively long molecular dynamic simulations, a single trajectory. Using things like folding at home, they've generated aggregate simulations where the total amount of simulation time is on the order of milliseconds, but it's composed of kind of thousands of independent trajectories on the order of nanoseconds to perhaps a single microsecond. So these are the scales that we're looking at. But as I said, the challenge is the timescales of the processes we care about, things like folding, still occur on the timescale of milliseconds to seconds. So even with kind of this massive computational power and advances in algorithms, we're still not kind of quite at the scales that we want to be to study these systems. So one thing to do, as Greg had mentioned, was we can coarse grain the system, we can represent it in a more coarse fashion, such as that HIV viral capsid, and then we can get to longer time steps and faster computations and see how those things assemble. But I'm going to talk about some methods where we take the actual MD simulations and try to build up a model that describes long-term kinetics. Okay, so what I'll be talking about today is the basics of this model that we call a Markov model. I'm going to first describe what exactly the model is, how we can use it to get at these longer timescales, and give you a few example systems. Then I'll talk about the algorithms for building these models. And as we'll see, this model consists essentially of a set of states and transition rates between them. And I'll talk about how we can define these states and transition probabilities from the molecular dynamics simulation. And at the end, I'll finish with a little bit about uncertainty analysis, how we can tell how accurate our models are, and how we can use those uncertainty calculations to improve our overall sampling. I'm talking about systems where we're really doing on the order of months of simulation. And so perhaps we can plan our simulations a little bit better, do some simulations, build a model, and then plan out our future simulations so that we can build the best possible model with the computational resources we have. All right, so the main idea behind a Markov model is we have the very large conformation space of our system. Here I've drawn in 2 dimensions, but this would consist of at least kind of the 3-dimensional positions of all the atoms of the molecule. Typically, we neglect the solvent degrees of freedom, and typically we neglect the velocities of the system, partly because for MD simulations, we often don't save those at every time point, and partly because we believe that those sort of decorrelate fast enough that we can neglect those and still be able to build a reasonable model. But what we do is we take that still high-dimensional conformation space, 3 times the number of atoms, and we're going to partition it into some number of discrete states. So these states could correspond to, they don't have to, but they could correspond to something like an unfolded region, a disordered region of the molecule, some folded native state, some very small region of conformation state, space that corresponds to a folded region, some intermediate, perhaps a helix is formed but a beta part hasn't, some trap state, things like that. They don't have to correspond to those, but you can sort of picture that's what these states would be. And then we're simply going to model dynamics as Markov transitions or history-independent transitions between these states. So we're going to say for some discrete time, often called the lag time or transition time, we're going to say if I'm in state 1 at time 0, what's the probability that I'm going to be in, for example, state 2 at time t? And that would be our transition probability t12, the probability of going to state 2 at time t, given we're in state 1. And again, these are Markov transitions, so we assume we don't care how we got into state 1. It doesn't matter if we came into state 1 from state 5 or state 3. We assume these Markov dynamics at this transition time t will tell us how we get to state 2 or state 3 and so on. So we believe that this could be a reasonable model. This Markov model could be a reasonable model because for simple chemical systems, they often exhibit this type of Markov stochastic behavior. So here I show a very simple system, the butane molecule, where the main degree of freedom of this molecule is rotation along the central bond. So what happens here is this CH3 group can kind of rotate up relative to the rest of it. And here is shown the energy of the system as a function of this angle. And we can see that the system has 3 energy wells, which correspond to these 3 states here, various chair and boat conformations, if I remember my chemistry correctly. And so instead of considering the system, the motion of the system as continuous along this degree of freedom, it's often very convenient to think of it as discrete, as 3 discrete states given by partitioning this energy function at these energy barriers. And then we can model the transitions as random transitions between those 3 states, and we can calculate the rate or transition probability between these 3 states. Implicit in this transition diagram is the fact that we're assuming that it's a Markov system. It doesn't matter if we got into the center state from this side or from this side, we're going to have the same transition rates to our other 2 states. So for simple chemical systems, we believe that this could be a reasonable model, that we can divide the space into discrete regions, and we can model the transition probabilities as Markov transition probabilities. But the challenge is trying to extend this to higher dimensions and trying to find these states and to find these transition probabilities in such a way that we're still preserving the overall dynamics of the system. All right, so if we can build a model, I'll show you in a little bit how we can try to build such a model. But if we can build such a model, there's a lot of things that we could then do with it. Because of the Markov assumption, we can very easily calculate long-time behavior of the system. So for example, let's say that we initially start with some probability of being in each of our states, states 1 through state n, at time 0. So that's given by this vector right here. We can easily calculate the probability of being in any of our states at time 1 by simply multiplying our initial probabilities by our transition probabilities. So for example, the probability of being in state 1 at time 1 is simply the probability of being in state 1 at time 0 times the probability of staying in state 1 plus the probability of being in state 2 at time 0 plus times the probability of transitioning from state 2 to state 1, and so on. And so this is just matrix algebra. We can calculate very easily the probability of being in any of our states at time 1. We can repeat this procedure multiple times, and we can easily calculate the probability of being in any of our states at time t as simply the matrix exponential of our transition matrix to the t power. We repeatedly apply this transition matrix, and again, times our initial state vector. And so what's shown here is a very simple 6-state model for the alanine peptide, which is an alanine residue capped on both sides. Very large-scale simulations of this molecule were performed, and people previously knew kind of the 2 important degrees of freedom, rotations, again, along these central angles, the phi and psi angles. So shown here is just binning the simulation data in those phi and psi angles. The darker red colors are more populous regions. The white colors are less populous regions. And so looking at this diagram, these authors manually decided that this is where they would draw boundaries. Kind of this is where those energy barriers would be between these states, and they defined 6 states. Then what they did was they took the model they would build from the actual simulation data for these 6 states, and shown here in pink, or sorry, shown here in these solid lines, are what the Markov model predicts, built at a lag time of 6 picoseconds for the long time behavior of the system. So in other words, they started, in this case, they said, let's say everything starts in state 5. What's the population of each of my states going to be at longer and longer times built from simulations at 6 nanoseconds? So they only had to do simulations which were 6 nanoseconds long, but they could project out to, here it's shown to 100 picoseconds. They compared it then, they also did a large ensemble of simulations of length 100 picoseconds, and shown here the points with the error bars are those simulations, what the populations were when they started everything in state 5. And you can see that the Markov model built from simulations of length 6 picoseconds agrees very, very well with the simulations of length 100 picoseconds. So we can get at the long time behavior without having to perform simulations of length 100 picoseconds. Is that sort of clear? I see a few confused looks. Are there questions, or are we okay? Okay. Okay. Okay, so using this model, we can get away with individual simulations, which are much shorter, but we can still get at these longer time scales. And so here I've shown you we could calculate the population of the states with time. It would be very easy to calculate the equilibrium probabilities of each of our states. That would just be kind of the infinite time extension of this, but we could easily calculate it from the first eigenvector of the transition matrix. People have also done some work where they mapped each state to different experimental observables. So they would say, for the conformations in this state, what would something like the fluorescence be? And then you could calculate from the model, this is what I would expect my fluorescence curve to look like over time by taking essentially a weighted average of those state observables. And then you could compare that with experiments. And so there are lots of things one can do with this at longer times than what the actual simulations are. Another thing that people have been doing very recently with these are looking at different mechanistic properties of the total simulations. So what's shown here are some Markov model built from a simulation of the pin-WW domain, which is an anti-parallel beta sheet. The total simulation was 180 simulations of length 115 nanoseconds. And the Markov model was able to calculate a folding rate on the order of 26 microseconds, which is 2 orders of magnitude longer than the total simulation time. So again, we can access much longer timescales than we have from the actual simulations. And that folding rate agreed, I think, within a factor of 2 of an experimental folding rate. So these things are accurate compared with experiments. What they then did was they used various graph algorithms. The Markov model they built had 50 states, and they used various graph algorithms to calculate flows through the graph from the denatured state to the native state, and they could calculate this whole network of folding pathways. So this is slightly in contrast to what Aaron had talked about yesterday with transition path sampling and things like the string method, which sort of assume a single reaction coordinate and transitions occurring essentially along that one reaction coordinate. With these types of models, you can get a whole network. You can have a diversity of different pathways, and you can calculate the relative probabilities of these different pathways. So on some simple systems, people have also shown that these models can, for example, if you have one very narrow but lower in energy path versus some broader paths, higher in energy, you can show kind of which paths are preferred for various temperatures using these types of models. You can kind of calculate relative fluxes along your different pathways using these types of models. So that's something else. There's a lot of things one can do with these graph algorithms to essentially look at the transition matrix as a large graph and find pathways and find various other things in this model. A few other example models that have been built in recent years. Again, the alanine peptide, which I already showed you, just showing it kind of pictorially what those 6 states looked like. This was a recent one on the NTL9 protein network model, which shows kind of the various pathways, and the larger arrows obviously indicate higher transition probabilities. Model was built for the villain headpiece, which is a 3-helix bundle. In this case, the states were just automatically defined as each of the 3 helices either being formed or not formed, and then the transitions between them calculated. And then the top one was a project which I had worked on lipid vesicle fusion. So this was a very large-scale simulation of 2 lipid vesicles, which would come together and fuse into a single vesicle. And in this, the Markov model analysis showed 2 different pathways to fusion. One which was a very fast pathway where the 2 vesicles would come together and fuse very quickly. And the second was a much slower pathway where the 2 vesicles would come together and form a hemifused state where the outside membrane had fused, but the inside membrane remained separate. And then on much longer time scales, these would fuse into the single vesicle. And that also agreed with some experimental results of sort of non-exponential kinetics for the fusion process for this vesicle. And so this type of analysis kind of lets you get at some of that information. Okay, so I told you about the Markov model and what we could use it for if we could build such a model. As I said, the challenge was that these systems are very high-dimensional. The number of degrees of freedom, we're talking about the 3-dimensional positions of all of the atoms of the molecule. So we can't really do things like they could do with the alanine peptide, where we can project down, where we know the important degrees of freedom, we can project down and find what those energy barriers are. So in general, people have different algorithms for trying to figure out how to define these states and transition probabilities directly from large amounts of molecular dynamics simulation data. So I'm going to give you, there's sort of variants on these algorithms for different ways that people build these models, but they mostly consist of 2 steps. And I'm going to describe those 2 steps in general and talk a little bit about various modifications people use. Okay, so the challenge is to try to find states such that the dynamics between these states are Markovian. So here again, I've drawn a very simple one-dimensional, well, I guess not too simple, a one-dimensional energy landscape where you can see kind of different height barriers. If I were to define my states as A, B, and C, we can see that state B is not really going to behave in a Markov fashion. For particles that come in from state C, they're likely to stay in this region, and therefore they're likely to transition back to state C, as opposed to particles which come in from state A, they're likely to stay in this region and then transition back to state A. So this violates our notion of history independent. The transitions out of state B depend on how they got in. So that would be a bad state definition. A good state definition would be something more like this, where the barriers are at the divisions between the states are at the energy barriers. And then if we come in from state C, on short time scales, we're more likely to be in this well, and we're more likely to transition back to state C. But we're going to equilibrate within state B on a faster time than it takes us to overcome these large barriers. So if we define states like this, it's likely that we'll get a time on which the system is Markovian, behaves with these Markov transition probabilities, such that we can still describe these global dynamics of the system. The challenge is that when we do molecular dynamics simulations, these again live in a very high dimensional space. And so the individual conformations which we sample, they're always different from one another, right? We're never going to sample exactly the same conformation more than once from these molecular dynamics simulations. So what we would like to do is simply say, well, this point, kind of these are the probabilities of where it will go next. I could run, let's say, 100 or 1,000 molecular dynamics simulations from a specific conformation and see where it goes next. But the problem is all of those endpoints, they're not going to overlap with anything else I saw. So what we need to do is we first subdivide into many structurally similar clusters. We're going to make the approximation that if 2 things are kind of close enough in shape, that they're going to behave the same kinetically, that they're going to have similar transitions. And this is an approximation that we just have to make because we're in this very high dimensional space. But we don't want to just do that. We don't want to just define our states based on structure, because we can have things like a chain like this would be structurally very similar to a chain like this. But because the chain can't pass through itself, they're kinetically very, very different from one another. So we don't want to only define structural clusters. We're also going to use the kinetic information that we have from the molecular dynamics simulations to also influence what our state definitions are. So I'm going to talk about these 2 steps, and these are the 2 main steps that people use in building a Markov model. Okay, so the first thing was to subdivide into structurally similar clusters. The initial methods for Markov models tended to work in low dimensions, and they used very simple methods that simply said, let's take each degree of freedom and let's just chop it up into little bins, just like I showed for that alanine system. And then each cluster is just going to be an assignment in each of the dimensions to one of the bins. So each of those little boxes would be one of my clusters. Right? That's pretty straightforward. Boxing is a very similar thing to binning. We just take each degree of freedom and we iteratively subdivide it. So here we subdivided it horizontally. Then each of the 2 clusters that we have, we're going to subdivide it vertically. Those don't have to be at the same space. And we're going to repeat. This results in fewer overall clusters, and we can also stop subdividing a particular region of space if it has too few conformations assigned to it, for example. The drawbacks of these methods are that the number of clusters are going to scale exponentially with a number of dimensions. So you could do binning in maybe up to like 3-4 dimensions, but once you get higher than that, you're dealing with a large, large number of clusters, many of which won't be populated, but it's not really a very efficient way to group your space. Another method that people use is to take the conformation space, the very high dimensional conformation space, and first project it down into some lower dimensional subspace. So these molecules, as I said, they we represent the space that they live in as a three-dimensional positions of all the atoms, but we know that a large percentage of that space the molecules can't actually reside in, right? We can't have bond lengths stretch too far, we can't have atoms overlapping, so they really live on a lower dimensional manifold of this high dimensional space. And there are methods that try to find this low dimensional projection that still maintains kind of the dynamics and overall distances between the conformations in the high dimensional space. And so I'm not going to talk about these too much, but there's various linear, such as PCA or normal mode analysis, methods for projecting down onto lower dimensions, or nonlinear techniques, things such as isomap, which are methods for taking distances in a high dimensional space and trying to project them down onto points in a low dimensional space such that the distances between those points are still preserved. So you could do that, and then you could simply bin the data in this lower dimensional space. So this was an application from 2006 of an SH3 domain protein where they found two embedded dimensions, and they could sort of preserve the overall dynamics of the system. Another method, and the most common method for building these Markov models, is to simply do clustering in high dimensions. So people have worked on clustering techniques in high dimensions to try to group together points in these high dimensions that are somehow similar to one another. These can be applied to lots of different areas, anything where you have lots of data and you're trying to group it together. And so just in general terms, the objective is you have some n number of data points. Again, I've shown it here in 2 dimensions, but we can imagine these in very high dimensions. And we have some desired number of clusters k. The goal is to output a set of k cluster centers, such that if we assign each data point to its nearest cluster center, the sum of squared distances between points to their center is as small as possible. So this would be one possible objective function. There's lots of different objective functions for clustering, but this is a very common one. The problem is that this is an NP-complete problem, which means that it's very unlikely that we're going to have a polynomial time algorithm for solving it. So it's going to be almost impossible to solve exactly, and people instead have various approximations to this algorithm. So yesterday, Greg had mentioned that for the force matching, that at the end of the day, what you had was a linear least squares problem, where you essentially had a big parabola and you're trying to find the minimum of the parabola. That's what's known as a convex optimization problem, and there's efficient methods for solving those. These problems are instead ones where you have kind of a very rugged landscape in the coordinates of these cluster centers, and you're trying to find a global minima, and it's very hard in general. So typically you have approximations that find local minima, but you really have no guarantee that you're at the absolute best solution. Okay, so one thing that we see from this is we need to somehow define a distance between our points and our cluster centers, or between 2 data points, depending on exactly what our algorithm is. And so for molecular conformations, we have to decide on what that distance is going to be. And there's a number of different choices, but the most common one is to just use the RMSD, or root mean square distance, between 2 conformations. So root mean square distance, we take the square root of the average, so we're dividing by n, of the sum of square distances of each of the corresponding atoms. So here are our 2 protein conformations, for example. We would take the sum of square distances from each of the corresponding atoms, divide by n, and take the square root. That's the RMSD. In general, what we do is we assume that rotations and translations don't really matter, that this thing is invariant in space. And so we try to find the rotation and translation that minimizes this RMSD function, and this can be done very efficiently. So this is, in general, what the distance metric is, though one could use some distance using internal coordinates or distance matrices or various other things to compare 2 conformations. So that's a piece that one has to define depending on how one believes the system works. All right, the most popular clustering algorithm is called Kmeans, and I just wanted to show you how it works. This is, again, a very popular choice in general and specifically for building these Markov models. So the algorithm is very simple. It simply initializes the k centers. So I told you before we had those k cluster centers. What we do is we initialize those somewhere in space. This can either be done by choosing k random points in our space, choosing k random points from our data set as the cluster centers. There's a number of different ways to do the initialization. Then it repeatedly does 2 steps. In the first step, it calculates the distance from every data point to each cluster center, and it picks the one, it assigns the data point to the one that's closest. So it calculates the distance to each of the K centers, and then it assigns it to the one that's closest. And then each of the cluster centers now has a number of data points assigned to it, and it simply computes its new value as the average of the points assigned to that center. You can show that this always reduces that sum of square distance from each point to the nearest cluster center, that each of these steps is going to reduce that sum of square distance. And so at some point, it will converge to something. Again, there's no guarantee that it's a global optima, but normally you stop when either the cluster centers stop changing, they're sort of fixed in space, or when the change in the sum of square distances is small enough. You're sort of satisfied that it works. Let me show you a very easy two-dimensional example, and then we'll talk about a few of the caveats when it's applied to molecular data. So here's K centers in 2 dimensions. Here's my input data, and I want to find 3 cluster centers. They randomly picked 3 data points to be the 3 centers shown here with the circles. They then assigned each point to the nearest center, which is shown by the different colors for the different data points. So they would calculate for this data point, for example, the distance to each of the centers, and they would assign it to the one that's closest. In the next step, they then calculate the average of, for example, all the red data points. So all my red data points up here, I calculate the average, and I move my center up there. I do that for each of my centers. And then I again calculate the distance from each data point to each of the cluster centers, and I reassign them. Yeah?
How minimalistic is the average structure might not be somewhere?
Yeah. So I'm going to talk about that. So this is in kind of Cartesian coordinate space in general for, or Euclidean space in general for data points, but there's definitely challenges with taking the average for molecular conformations, and I'll talk about what people do in practice. All right, but so you can see that kind of the centers are moving towards these high density regions, and at some point they're essentially, the assignment of data points to the cluster centers is stable, and that's when we would stop the algorithm. So as you mentioned, one of the things that is challenging for molecular data is computing these cluster centers as the average of points. If we average molecular conformations, there's no real guarantee that the average conformation is going to have any meaningful interpretation. You could end up with an average that has kind of bond lengths and angles that are kind of way out of whack from what is normal. And so the modification that people often use is an algorithm which is essentially the same. It's called Kmeadoids. And in that case, what you do is here, instead of computing the cluster center as the average of points, you instead sample from the points within the cluster center, calculate the sum of square distance, and pick the one that has the smallest sum of square distance. So you restrict yourself that the centers always have to be data points. That gets over the problem of unphysical cluster centers, but it is more computationally expensive because calculating the average of your points is much easier than if you have 50 points having to calculate the distance between all pairs of those. So often this is done as kind of a sampling approximation, and you find something that's reasonable. And again, you can show that it's always improving. It always has to decrease because you have some current center, and you're always going to do at least better than that, but it might decrease slower. So that's one caveat that you have to take into account for molecular data. The other thing, as I mentioned, the energy landscape of this algorithm, the objective function we're trying to minimize, is very rugged, and so there's no guarantee we're going to find a global optima. And you can see that this is essentially a deterministic algorithm, so the local optima that we fall down to depends on the initial centers. So what people do in practice is you normally run this algorithm multiple times with different initializations and then take the overall best one. And that's sort of the best approximation you get to a global optima. But again, it's no guarantee. So normally you would run this multiple times with different initializations and see how you do overall. Okay. So I've described how we can take our conformation space and use one of these clustering algorithms to break it apart into these structurally similar groups. We want the dynamics to be Markovian. So typically, the orders on which people define the number of clusters is on the order of thousands to tens of thousands, so that we're sure that we don't have kind of large energy barriers within these states. We could just take these 10,000, for example, clusters and calculate the transition probabilities between them from our molecular dynamics simulations and perform all those analyses that I had talked about, such as calculating the populations of the states with time, calculating different pathways, and various other things. But there's a few reasons why people normally do the second step, this kinetic clustering step. And the first one is that it's often very hard to interpret a model with 10,000 states. I give you a model, here's 10,000 states, it can reproduce the dynamics, and you say, okay, now what do I do with it? I need to somehow understand what's happening. I want to see kind of what these pathways are. I want to see kind of what these different states represent. It's often challenging to do for a model with 10,000 states. The other piece that I'll talk about a little bit later in the talk in more detail is that the statistical uncertainty is going to grow with the number of states that we have. If we think of the parameters in the model, the parameters are essentially those transition probabilities. So for a model with 10 states, we would have 100 transition probabilities that we have to estimate from our data. For a model with 10,000 states, we would have 100 million transition probabilities, is that right? A large number of transition probabilities. Things aren't quite that bad. In general, these models will have rather sparse transition matrices. It's not that you can kind of get all the way from a massively unfolded state to a completely collapsed state in a picosecond. But we still have larger number of parameters to estimate. So the motivation for the kinetic clustering is, well, I have this large number of groups of conformations that are structurally similar. My goal was to define a model such that transitions within each state were fast and transitions between states were slow. So I want to group together these structural clusters exactly to satisfy that criteria, so that transitions between these states that I define are going to be rare. If that's the case, then when I transition into a state, it's more likely that I'll equilibrate within that state, forget where I came from, and then the transition out of that state will be rare, and I will satisfy that Markov property. So that's going to be our goal, to group together these structural clusters so that the transitions are rare. The one thing that I haven't really told you about so far is how to actually calculate this kinetic similarity, how to calculate these transition probabilities. And this is, it's not very complicated, which is sort of why I skipped it till now. So we want some similarity measure between clusters that says how likely is it to transition between them. Now that we've grouped our conformations into these structural clusters, each of these structural clusters will have some number of conformations associated with it. And so we can simply calculate for the things within that cluster, where do they go at the next time point? And I can calculate that as I can make that equal to my transition probability. This ends up being essentially a Monte Carlo estimate of the transition probabilities, where I simply count the number of transitions from state I to state j, and I divide by the total number of transitions from state I. So we simply take the average, or the probability of going to a different state j from, given we're in state I at a certain time point. And we can build this at some lag time tau, which I had mentioned before. All right, there's one very minor caveat there, that we assume the samples within each state sort of follow the same distribution. We can't sample, for example, all of our samples from state 4 from this little region. Then we'll get a very biased view of the transitions from state 4. We would need them to follow the correct distribution from state 4 to use this Monte Carlo estimate. But in general, our molecular dynamics simulation should satisfy that property because we assume within state 4 they equilibrate quickly. So that's a little thing that you have to be concerned about if you're sort of, when we get to biasing our simulations. We can't just start them kind of all from a single point within the state. We need to sample them broadly from within the state. All right, so the method people use, and I'll say on the next slide why exactly we use this method, is a method called spectral clustering. And this is, again, another general purpose clustering method. I believe it was developed in the late 90s. And one of the first applications was to image segmentation. So in that case, you have the points in space would be pixels in an image. And you would define some similarity between neighboring pixels based on how similar in color they are. And you want to somehow subdivide your image into groups such that the different groups correspond to different things such as foreground and background. And so typically you have some points in space. You define a similarity between those points. Here they define similarity as the k nearest neighbors, so the 5 nearest neighbors of each data point. They simply connected with edges of weight 1. You could define some type of Gaussian distribution function, so everything is connected, but with smaller and smaller weight as you get farther apart. The goal is then to find a cut of the graph. So I want to somehow chop up my graph such that I cut the smallest weight, smallest total weight of the edges. So in our image, we want to divide our graph such that pixels that we divide between, they are dissimilar in color, right? Because those will have small weight. This problem for larger than 2 subdivisions is another one of these NP-hard problems. So people have various approximations to it. Typically, there's also some modifications to the algorithms that say I want my partitions to be balanced, because oftentimes the smallest cut you can get is sort of chopping off points at the edges and just leaving everything else grouped together, because that'll give you a very low weight cut. And so instead we say I want the number of points in each cluster to be somewhat balanced, and that's called the balanced n-cut problem. And there's various, again, approximations to that. In the literature that dealt with spectral clustering in computer science, they also formulated this exactly as a random walk over the edges. So it said, I have these similarity edges. What if I consider this as a random walk where I start at any point in my space, and then I take a random step with probability proportional to the weight of that edge. And they showed that this would minimize the number of transitions between the clusters that you defined. So if I take kind of random walks here, I'm going to stay in this part of space, and I'm going to rarely transition over to this part of space. And that's exactly the property that we wanted for partitioning our structural clusters that we had defined. We wanted transitions between our clusters, our states, to be low, transitions within each cluster to be high, and that's what's going to happen with these spectral clustering algorithms. We're going to have, if we find these cuts in the graph, we're going to have transitions between the different cuts small, and transitions within each cut to be large. All right. So the way these algorithms work, just to give you a little bit of flavor, we could use other clustering algorithms on this similarity graph. The challenge is that things like Kmeans can only define what are called convex regions in input space. So for example, if these are my data points, we can see I have 2 very clearly defined clusters, this inner blue circle and this outer red circle. But if I do the Kmeans algorithm and I try to stick 2 cluster centers on there, there's absolutely no way I can define these 2 clusters given this input space. If I put my 2 points here, the partition between my 2 clusters will always be drawing an equidistant line between those 2 clusters, and points on one side of the line go to one cluster, points on the other side go to the other cluster, and I can't get these 2 circles out. So instead what we're going to do is we're going to take the data points, we're going to project them onto some other space, and the hope is that once I project them onto some other space, I then will be able to draw nice convex regions in that other space such that I subdivide my clusters. So this is very similar to what was talked about yesterday, the PCA method for calculating those modes of motion. We're going to do the same thing. We're going to project onto the top k-dimensional eigenvector space. And the idea is that the slowest eigenvalues will define the slowest modes of motion on this random walk on this graph. And values, if we look at the corresponding eigenvector, we'll see kind of a sign difference between the changes in those modes. We'll have positive values for things on one side of the mode and negative values for things on the other side of the mode. And if we look at the top k-dimensional eigenvector space, we're going to have points which transition very fast, points which aren't involved in any of those top k motions. They will have similar values for their eigenvector components. And points which are separated on those timescales, they'll have different values for those eigenvectors. So we're going to take this, we're going to project it onto the eigenvector space, and we're going to perform some clustering algorithm in this space. Typically, this could be something like K-means on this space, and we'll see that our points are very well separated in this space in general. And then we obviously assign those back. And so this is how spectral clustering works. In general, again, there's a few modifications of the algorithms that people use, a few kind of different variants for what exactly do you use as how exactly do you construct your transition matrix, how exactly do you do your clustering, but this is the basic flavor for how it works. Okay, are there any questions? All right, so that was the main method. So I wanted to tell you now, just show you 2 quick examples for applying these to real data, and then talk a little bit, we're getting close to out of time, so a little bit on error analysis methods. So the first example was one that I had already showed you, the simulation data of this alanine peptide. So again, this one's a nice one to show just because we can visualize it in 2 dimensions. So this was kind of the sampling of points according to this large molecular dynamics simulation. They then took the points and binned them in this phi psi space. So again, just counting the number of conformations which lay in each little bin and color coding according to the density of points there. This is like a potential of mean force. And then defining the states based on energy barriers between various regions of space. They had previously identified these 6 states which they thought the system held. And our goal was to apply an algorithm which didn't know about these important degrees of freedom phi and psi, which instead would do clustering in the entire high-dimensional space of the molecule. I think there's around 20 atoms, so around a 60-dimensional space. So we're going to try to do clustering in 60 dimensions and try to reproduce these states. So our first attempt at doing this, what we found was this lovely picture where these were our states. We found kind of some of the states were nicely subdivided. These ones sort of correspond to regions. But we had this horrible black state that basically sat on top of the other states. But when we actually looked at those conformations, what we saw was that the black state corresponded to a very unusual torsional bond. It was a rotation along this torsional bond, the omega torsional bond, which doesn't occur very often. So in the simulation data, there actually was this separate conformation, which when projected down onto phi psi space, overlapped a lot of our conformations and did have very, very long timescales associated with equilibrating between the different omega bond conformations. So you could recapture that, yes, there is this additional weird omega state which had long timescales, and it could find that using these methods of going back and forth between the structural clustering and then the kinetic clustering. So this is one of the benefits of not kind of projecting down onto some lower dimensional space ahead of time, that you could find things that you don't know are there. Yeah?
Are the black points that are on top of the pink actually converting quickly, the black with the other?
Quickly compared to how slow they converted with the rest of the phi psi space. So in this, we told it to find 6 states. I would assume if we told it to find 8 or 10 states, it may have subdivided the rest of the black states. All right, as another example, we looked at a trypsit peptide, which is a little beta hairpin, and people had previously defined states based on the hydrogen bonding pattern. So kind of here's the peptide, there's a normal hydrogen bonding pattern, and then the 2 ends of the hairpin could sort of offset by 1 or 2 residues and form hydrogen bonds between different residues in the, on the 2 strands of the hairpin. And so these were the states that had been previously defined based on hydrogen bonding patterns. When we applied the algorithm to this data, we found kind of this whole zoo of different conformations. And we can see additional resolution in the folded state, which is that top state. The one with native hydrogen bonding patterns, we then saw different packing of the 4 tryptophan residues, which are what sort of define the state. So we can see kind of very clear packing. We can see, again, sort of these states also differed in the packing of the tryptophan residues. And in the unfolded state, we had a lot of resolution of various states. I think these ones were offset by 2 or more hydrogen bonds. Some of these states, we saw some that were alpha helical-like, and then some which were just kind of very unfolded and very like hairpin-like, but not really collapsed into any order. And these, again, these are kinetically meaningful states. These are ones that tended to be long-lived compared to the overall dynamics of the system. So, yeah, one of the reasons that I like the Markov model is that you don't have to put a lot of information into it in terms of what you believe the mechanism is or what you believe the different states relate to. It can find states that are just kinetically different from one another that describe the long-time dynamics of the system. All right. So the last thing that I wanted to talk about was how we can now use these models to improve our sampling. So first of all, we have to talk about what we mean by improving the sampling, and specifically we're going to try to reduce the error in the model. So we need to talk about how to calculate the error and then how to improve our sampling to reduce that error. All right, so once we've defined the state, so in this uncertainty analysis, I'm going to assume that our state definitions are correct. People have also looked at the problem of what is the uncertainty when your state definitions are not quite right, when you have kind of those boundaries are not right where they should be, what happens then, and that's a little bit more complicated to explain. So I'm going to focus on the case where we assume we know the state definitions, and we're only going to be concerned with the uncertainty caused by estimating our transition probabilities. If you remember, we estimated our transition probabilities as, for example, the transition probability from 3 to 5 is the number of transitions from state 3 divided by the total number. And you can see in these two sets of simulations, in one case we would estimate the probability from 3 to 5 as 2/5, and in one case we would estimate it as 3/5. But these are, if I do 5 simulations, they're both reasonable numbers. And these would give us different things we calculate from the model. I don't think I talked about all of these, but we could calculate something like the average, the mean first passage time, the average time to get from one state to another, the p-fold, the probability of being in a state and getting to the folded state before the unfolded state, and things like the eigenvalues and eigenvectors. I'm going to focus on the eigenvalues, and specifically the first non-unit eigenvalue, which corresponds to the longest rate in the system, because that oftentimes corresponds to the folding rate of the system. All right, so as I said, when we calculated the transition probabilities, we simply counted. We said the transition probability from state I to j was the number of transition probabilities from I to j divided by the total number. That gives us essentially a maximum likelihood estimate of that transition probability given our data. But instead, we can use Bayesian analysis to talk about the entire distribution of possible transition probabilities. So if here is my parameter Tij, the probability of going from I to j, we know it's bounded between 0 and 1. And if, for example, I saw 30 transitions to k and 70 to j, I would be peaked around 0.7, but I would have kind of some broad width of reasonable values that I would say, that could be likely. If I saw more data, if I saw 300 and 700, my maximum likelihood value is again still the same, but now I'm not really going to believe you very much if you tell me the transition probability is 0.6. For example. So these distributions will change depending on the amount of data we have. And specifically, we can calculate this distribution using Bayes' rule. The probability of a given value for the transition probabilities, given the data I see, is proportional to the probability of the data given the transition probability times some prior over the probabilities, the transition probabilities. And yeah. So what I'm going to show you is you can always calculate them. What will happen if you have very low data counts, you'll end up with very broad distributions. And then we'll calculate the uncertainty in, for example, the eigenvalue, and we'll see that will have a very broad distribution also. And that will tell you, I can calculate this rate, but I don't, it's got a huge range for which are plausible values. Yeah, so it's not very important, but what we end up doing is we pick the prior over the transition probabilities to be a prior distribution called a Dirichlet prior distribution. And the reason is because if we multiply that by the probability of the data given the transition probability, we end up also with a Dirichlet probability, and that's just to make the math really nice. All right. I'm going to skip this because basically what we do is to calculate the eigenvalue, we do a Taylor series expansion and get a very nice closed form distribution for the eigenvalue. We use that closed form to calculate where should we do more simulations. So the problem is simulations are really expensive. Even with things like this distributed computing, the supercomputing, we still run these simulations for many months. And we want to start our simulations intelligently so we can calculate whatever properties we want from them. Typical approaches to sampling are things like equilibrium sampling, where we sample each conformation from its equilibrium distribution. If we run single very long trajectories, they will tend toward the equilibrium distribution, right? So if you have a single trajectory that's very, very long, you would expect it to sample points according to the equilibrium distribution. Another common strategy for something like the Markov model is to just start the same number of simulations from each state. So for example, for the alanine system, once they built that 6-state model, they simply started 1,000 simulations from each of the 6 states. That would be another very common strategy. So I'm going to talk about some new sequential approaches that use the error analysis to figure out where to start new simulations, and then use those new simulations to figure out where to start, again, new simulations. So this I had sort of glossed over. When we actually calculate this closed form distribution for the eigenvalue, what you end up with is the eigenvalue is some mean approximation given the maximum likelihood values plus some variance term. The variance term depends on the sensitivity to, so the change in lambda depending on the change in the transition probability, so it depends on the sensitivity to the different transition probabilities, as well as the uncertainty in the different transition probabilities. So delta T11 says how much would I expect my transition probability from state 1 to state 1 to change if I added more samples. And we can see that, I could have states where these deltas are very, very large, and they will calculate a large amount to my uncertainty, and therefore I should start more samples from them. But if my eigenvalue, if my rate of folding is unsensitive to those, I don't need to start more simulations there, right? If I have some main pathway and I have a state way up here that nothing ever goes to, even if I have very uncertain transition probabilities, it doesn't affect my rate of folding. And so it's a balance between these two values, the uncertainty and sensitivity, and we can very easily calculate the expected decrease in my overall variance of my rate and start simulations from the one that will decrease it the most. So this is what I call the adaptive sampling. And one can show that kind of using these 3 simulation strategies, equilibrium sampling, so this is the total number of trajectories and the uncertainty in lambda, even sampling where we start the same number from each state, and adaptive sampling, this is on a log scale, so adaptive sampling gets sort of an order of magnitude improvement over even sampling for this 6-state system, and one can show that as the number of states increases, this, I've shown kind of 2 or 3 orders of magnitude difference here. So in terms of simulation planning for very large-scale simulations, I think the Markov model is a really powerful tool to figure out where one needs to start the simulations to really explore the space. And it also shows that kind of these methods that do single long trajectories, they're really sampling a lot from the energy wells. That's where the equilibrium samples tend to be. And you've already sampled those very, very well. They're very well established. And as relates to what Aaron had talked about yesterday, you really want to sample the rare events. You want to sample the ones that you don't see very often. And so things like this adaptive sampling will, again, sort of bias you towards sampling those events more often. All right, just a very brief summary slide that has nothing new. So Markov models are just tools that we can build from large-scale molecular dynamics simulations. We can use them to model long timescale dynamics, and one of the benefits is that the input MD simulations can be orders of magnitude shorter than the system equilibration times and the timescales which we want to understand. And the main algorithms for building these models use both the structural similarity and the kinetic information encoded in the MD simulations to define the states. All right, thank you. Any questions? Yeah. Oh, yes. So the analysis was done, it was a 2000, it's called Automatic State Decomposition, is the name of the paper. It's a JCP paper. So the lead author is Chodera, C-H-O-D-E-R-A. It's either 2006 or 2007. Sorry, I didn't include that one. Yes? So I think one of the reasons it works is that molecular dynamics simulations should automatically sample from the relevant parts of conformation space. So if there are parts of conformation space that are relevant that the simulations never reach, so for example, if there's 2 main pathway channels and you just happen to never simulate the second one, yes, these would give biased results. And there's, I think, not much to do about that, but I don't know if MD methods in general overcome that problem So I think the hope is that the molecular dynamics simulations should sample the relevant parts. And then things like the error analysis could tell you, you've gotten to this region of space, but you have very little for where you go next. And those should hopefully fill in the rest. Yeah, I'm sorry, I'm having a hard time hearing you. Yeah, I think that's a problem for a lot of MD techniques, that if there's parts of space that are not sampled, then there's nothing much to do about it. I don't know if there are I'm not sure what solutions would be for that. Yeah.
Once we get the transition matrix, but once we have that, I'm wondering what kind of...
So from the Markov model itself, you can go out to infinite timescales, right? You can keep repeatedly applying it. And so the hope is that the time scale on which your transition matrix is, so for the alanine example, it was 6 picoseconds, that is kind of at least an order of magnitude shorter than the global equilibration time. Right, because the Markov model will let you describe processes in between those two scales. Once you get out to global equilibration, your dynamics it'll just be flat, right? Your population of states will stay the same. And so you hope to capture something about that intermediate process between the internal Markov equilibration time, the time it takes to equilibrate within each state, and the global equilibration time. So that's the goal, to get that as large as possible.
And computationally as well. The cool thing is it's just multiplying by matrix.
Oh yeah, that's kind of nothing.
So, yeah,
I think even for models. Oh yeah. Even for models where people build like 10,000 states, I think matrix multiplication, they're pretty fast operation.
Yeah, that's
so
yeah. That's a really cool thing about it.
Yeah. Yeah, definitely. So that is sort of an ongoing thing. With the spectral clustering, in theory, what you can do is you can look for gaps in the eigenvalue spectra. And so that should say kind of, I have so many processes that occur on this long time scale, and then I have a gap, and these other processes happen faster. For simple systems, people see these eigenvalue gaps. For more complex systems, there's often more of a continua, and it's sort of arbitrary where you decide to cut it off. And yeah, I've done a little bit of work trying to balance the number of states based on how much data you have, which I think is also important. It might be that I really want 10 states, but I don't have enough data to parameterize that, and I'm better off with a model with 4 states that, is slightly lower resolution, but is more accurate. So that's sort of the one that people tend to use, is looking for these gaps in the eigenvalues. Okay, thank you.